Alessandro.
Thank you very much for a great talk, and it's my great pleasure to introduce Daniel. Daniel is a very fresh PhD graduate, so he completed his PhD in 2019, which is actually now 2 years, although it feels it was just a couple of days back. He's now a professor at University of California at Santa Cruz. And I have to, Daniel, refer maybe more to your PhD achievements. When Daniel was a star student, his advisor at Berkeley, his advisor was Sansi Sheshia, Daniel managed to get all sorts of awards. He got like a Distinguished Researcher Award from University of Berkeley. He got NSF Graduate Research Fellowship, which is a very prestigious fellowship given only to the best applicant. He got Best Paper Award at Conference on Internet of Things. So without further ado, since we are a little bit behind the schedule, Daniel, I give floor to you, and I'm looking forward to your talk.
Thank you, Ruchika. Can you see my slides?
Yes, we can see your slides.
Okay, great. And I will try to stay on time here. All right, so hi, everybody. I'm Daniel Fremont. Today, I'm going to talk about algorithmic improvisation, which is a mathematical framework for synthesizing randomized systems. So why do we care about randomization in systems? So Just Peter gave a great example earlier of using randomness to get robustness that would not otherwise be possible in a deterministic protocol. But there are actually many reasons why systems use randomness, in fact, depend on randomness to achieve not only robustness, but maybe variety or unpredictability. So let's look at some examples from very different areas. So one would be, suppose you have some neural network which is supposed to take images like these and detect objects in these images. And you want to generate training or testing data for this network. So the task is to generate images of bumper-to-bumper traffic, say. That's a huge space of possibilities. These three images are very different from each other, but all meet that high-level description of bumper-to-bumper traffic. And we can use randomness to cover that space evenly. We'll come back to this example later. Another reason why you might need randomness is realism. So for instance, let's say you want to design a lighting controller for a house that mimics the user's typical behavior when they're on vacation. If you had a deterministic model for that, it would be unrealistic because human behavior is inherently random. Some days you wake up a little bit later, some days maybe you cook more or less. And so you really need a stochastic model to faithfully represent the human's behavior. A third example would be using randomness for unpredictability. Say you have some surveillance robot that's supposed to patrol different rooms in a museum. It's got some other constraints, maybe, has to recharge, these kinds of things. If you solve those constraints, you found a policy that was deterministic and you had a single route for patrolling the museum, then it might be that every night at 2 a.m., the robot's at one end of the museum and the thieves will break in on the other end of the museum. But if you used a random route, that would make the robot's future prediction harder, future location harder to predict. While at the same time, of course, we still want a correct by construction plan. So we'll also come back to this example. But the point to see is that in all of these systems, randomness is really essential for the proper operation of those systems. But at the same time, they need to satisfy formal specifications. So in the lighting control example, maybe you want to use at most a certain amount of power each day. In the image generation, you have realism constraints, like objects should not intersect, for instance. And in robotic planning, you've got safety specifications, like don't collide with some other drone that's moving around in the same space. So there's this general question then of how can we design a system that uses randomness, but still has controlled behavior? So how can we synthesize a system that can make use of randomness? And that's what algorithmic improvisation is really about. It's a framework for automatically synthesizing systems, which could be reactive systems, that have a random behavior but formal guarantees. So like in ordinary correct by construction synthesis, we have safety or other guarantees which have to be satisfied. The new thing is we also have a guarantee of randomness. So we'll have some constraints saying the behavior of the system has to be random in some sense. And the fundamentally new thing here is that randomness is really part of the system's specification. And that makes this a different problem from, say, reactive synthesis that's been studied a lot. And so we really do need new techniques, although, as we'll see, we'll build on classic work on synthesis and on uniform sampling from constraints. Okay, so just to outline this talk, I'm going to start by defining kind of the core computational problem in this area of algorithmic improvisation, which we call control improvisation. And I'll illustrate that with some examples. And then I'll give you a quick overview of the theory of this problem that we've developed, both efficient algorithms and complexity hardness results. And then I'll talk in a little bit more detail about an interesting application of this area that we've been working on the last few years, of using improvisation to design and analyze autonomous systems, particularly systems that use machine learning. And finally, I'll wrap up with some directions for ongoing work. Okay, so to start with control improvisation here. Oops, animation, silly there. All right, so to motivate the definition, let me go into a little bit more detail about this robotic surveillance example that I mentioned before. So if the task that you have is to patrol an area in an unpredictable way, you have various different types of specifications. So you want to do a correct by construction synthesis, but what are the specs for that synthesis? So you have a typical type of specification, like maybe you need to visit each of these various locations that are important sufficiently often. You know, the typical type of spec we could encode in LTL or something like that. You might also have a constraint like take a route close to the shortest one. Maybe you don't want to take the shortest one because maybe it's unique and then there wouldn't be any unpredictability, but it should be fairly close to the shortest possible route. And then you might have a yet third type of constraint saying, don't always take the same route. We actually want some unpredictability in this. And the thing to notice is that these are three very different types of constraints. The first is what we call a hard constraint. This is something that has to be true all the time. Whereas this constraint only needs to be true to some extent. It's sort of a soft constraint. And this third constraint is not a constraint on individual behaviors at all, but it's a constraint on the distribution of behaviors of the system. So in this application, and it turns out in quite a few other applications, so the couple that I mentioned before, but some others that I won't really get into in this talk, like music improvisation, which is where the name of this problem came from in the first place, also software fuzz testing, other things like that, they all have this same type of form of you want to synthesize some sequence of actions or decisions, something like that, subject to three different types of constraints. A hard constraint, which everything you generate has to satisfy. A soft constraint, which most things you generate have to satisfy. And some randomness constraint saying you can't just generate the same thing over and over again. And there wasn't really a problem already in the literature that simultaneously captured all three of these. And so that's why we defined this new problem we call control improvisation. The idea is it gives a precise, grounded definition that lets you study synthesis problems of this form. So let me introduce a bit of notation before we can define the problem. Let's think about this robotic planning example. So maybe you have a drone over here that's supposed to visit these 4 circles while avoiding maybe some other drone here. We'll come back to that later. And maybe it has to avoid this central spot as well. And we'll say that the plan for the robot will be described by a sequence of actions it could take moving in this grid world. So we'll have a finite alphabet sigma of 4 actions from moving north, south, east, and west. And let's say we want to generate a plan of length 30. So 30 of these actions. I'll just say fixed length for simplicity, but we can also handle, up to some bounded length. Our hard constraints will be given by some specification H, where I'm being deliberately vague about what I mean by specification. It could be temporal logic, it could be an automaton. The complexity of the problem will depend on what type of specification you have. So here, the example could be visit all of the 4 circles while avoiding collisions with this other robot. That could be our hard specification. And we'll have our soft constraint given by another specification S, which in this case, let's say it's don't visit the same circle twice, because that would be redundant. So we don't want to do that too often. Okay, so now given these specifications, H and S, for the hard and soft constraints, we'll define a few sets. So if we think of the universe of all possible sequences of actions we could generate, so this is sequences of n symbols from this alphabet sigma. This includes trajectories like this, where maybe the two robots collide with each other. So that is not allowed because that violates our hard constraint. So we're going to pick out a subset of this space, which is the subset satisfying this hard constraint H. So they're in the language of that specification. We're going to call those the improvisations, or this set I. Now that set also contains things that are safe. Maybe they satisfy the hard constraint, but they violate the soft constraint. So like here, this path visits this circle twice. So we're going to call that an inadmissible improvisation. And we'll have a further subset A of admissible improvisations. These are the ones that satisfy both the hard and the soft constraint. So here, for an example, this plan visits all 4 circles, and it doesn't visit any of them twice. So that would be an admissible improvisation, and that's in this set A. Right? So keeping this picture in mind of these different sets, now we can set up the definition of a control improvisation problem. So given the hard and soft constraint, this length-bound n, and a couple of other parameters. So we're going to have an error probability epsilon, which is going to say basically how often you're allowed to violate the soft constraint, and some probability bounds lambda and rho that will be used to constrain how much randomness there is, as we'll see in a second. We'll say that a distribution over words is an improvising distribution if it satisfies 3 conditions. So the hard constraint says that if you sample a word from this distribution, it has to satisfy this hard specification H. That is, it has to be an improvisation with probability 1. The soft constraint is similar. It says if you sample a word, it has to be an admissible improvisation. So in this further subset A, most of the time. So at least 1 minus epsilon probability. So you can tune how tight this constraint is by picking epsilon. And finally, to enforce randomness, we'll say that every word that you could generate, so every improvisation, its probability has to be at least lambda and at most rho. So this would allow you, for example, to say that nothing is generated too frequently by picking some small value of rho. So if you picked rho as 1 in a million, then nothing can be generated with probability greater than 1 in a million. In this talk, just to simplify things, I'm going to assume lambda is 0, but you can check out our papers for the more general definitions. OK, so given all of this data, the hard and soft constraint specifications and these parameters, we call that an instance of control improvisation. And we say it's feasible if one of these distributions exists. And then what we want is an algorithm that samples from such a distribution, which we call an improviser. And so the synthesis problem here is, given one of these instances, given the specifications, construct an improviser, an algorithm that samples from a distribution that satisfies all of these constraints. And the reason why this might be difficult is that these sets, I and A, might only be described implicitly, maybe by a Boolean formula or something like that. They might be exponentially large, so we can't just enumerate these sets to come up with our policy. So let's look at an example. Suppose, for instance, you had 3 different admissible improvisations and 2 other improvisations which were not admissible. Then if we set epsilon and rho to 1/4, for instance, so this would be saying you're allowed to violate the soft constraint 1/4 of the time, and no individual improvisation that you generate should have probability greater than 1/4, and we'll say lambda equals 0, then this is an example of an improvising distribution. Pick one of these 3 behaviors with probability 1/4 each, and one of these 2 other behaviors with probability 1/8 each. And if we did that, then that satisfies the hard constraint because we're always generating one of these 5 things. That's an improvisation. We're not generating anything out here. It satisfies the soft constraint because we get something that's admissible with probability 3/4, and we have epsilon equals 1/4. And no individual behavior is ever generated with probability more than 1/4, which was rho. So this would satisfy our 3 constraints, and so it would be an improvising distribution. OK, so this is the definition of the problem in the static setting. Now, if you want to do reactive synthesis, now we have to generalize this a bit because we have an adversary. So just briefly outline how we change the definition I just gave. So suppose now, same kind of example we had before, but now this other robot, maybe you don't control it. It can move around arbitrarily, and you need to make sure you avoid collisions anyway. So we will now set up the problem as a two-player game, as we saw in earlier talks this morning, standard formalism in synthesis, where the system and the adversary alternate picking symbols or actions at each step. We'll still have all three of those constraints, the hard, the soft, and randomness constraint, but now they need to hold regardless of what the adversary does. So we'll say for all possible adversaries, those three constraints still hold. And now our notion of an improviser will become an improvising strategy. Instead of just sampling from this distribution all at once, it will pick one action, and then it takes as input the environment's response, and then it picks its next action, and so forth. And once you do this, this gives you a way to do reactive synthesis in a randomized manner, at least for a bounded time interval. So as an example of that, we saw these animations before. What these were actually showing are some simulations using our algorithm for RCI that I'll talk a little bit about later, to solve this kind of surveillance problem where the robot in the bottom left is the one we're controlling. It has to visit these 4 circles while avoiding collisions with an adversary, which is the blue dashed line. And just to show you the randomness, in all 4 of these simulations, I've had the adversary move in the same way on the grid world. And because of the physics, it's not moving in exactly the same way each time, but it's making the same path through the grid world. And you'll see that our improviser, the black line, is responding in a very different way each time while still satisfying all of these constraints that we see on the left. And here we were actually using a randomness requirement saying, make rho as small as possible while still satisfying the other constraints. So in some sense, this is the maximally randomized policy. And our algorithm actually allows you to compute this smallest feasible rho. OK, so this gives you an idea of the problem definition. And now let me tell you a little bit about the theory of control improvisation. Oops. OK, so the first question you could ask is, when can you solve one of these problems? And it turns out that feasibility just requires these sets I and A to be large enough, at least with lambda equals 0, which is what we're talking about here. So in particular, a CI instance with lambda equals 0 is feasible if and only if these 2 sets are sufficiently large. And the idea behind these inequalities is basically that if these sets are too small, you may be able to solve the problem, but not in a random enough way. So if there's only one way to solve the constraints, for instance, then you can't possibly have a random strategy because you have to just generate that one thing that satisfies the constraints. And so the analysis basically shows you how you need to trade off the size of these sets versus the epsilon and rho that you're requiring. And where this proof basically comes out of, or it's kind of a consequence of this proof, of the construction we use in the proof, is that we actually can give a quite generic algorithm for doing control improvisation that doesn't really care about what the constraints are represented as long as you can implement a few abstract operations. So if you can efficiently intersect and take the difference of 2 specifications, restrict one to a given length, and then more interestingly, count the number of words that satisfy a specification, and uniformly sample from those words, both of which could be highly non-trivial. For example, if the specification is a Boolean formula, then this is the model counting problem or the uniform generation problem. But if you can do all of these things, then there is a polynomial time. If you can do all of these in polynomial time, then there's a polynomial time synthesis algorithm. And the way it works is we use these first 3 operations to construct those sets that we need. These sets I, A, and I minus A, so the inadmissible improvisations. We construct specifications for those. We can count them and then check those inequalities on the previous slide. If they're not satisfied, then we know the problem is impossible to solve. If they are satisfied, it turns out there's a very simple way to do the sampling to get an improvising distribution, which is you just pick uniformly from either the admissible or the inadmissible improvisations with the right probabilities. So you flip a weighted coin to decide which of these 2 sets to use, and then you sample from them uniformly at random. And if you pick the right weighted coin, you will satisfy all of those constraints we had before. So this, again, is for the static case. And now we can plug into this general procedure techniques for counting and sampling when we know how to do those efficiently and get algorithms. So for example, we get polynomial time improvisation schemes for deterministic finite automata, which are useful for examples in, say, music, robotic planning. We can use classic techniques for counting and sampling from automata here. Likewise, say if you want to do fuzz testing for testing some software, maybe from generative fuzz testing from a grammar, you might want to use as a specification a context-free grammar. And if the grammar is unambiguous, then again, we get polynomial time algorithms using techniques for sampling from grammars. So this is the kind of picture we get, that if the hard constraint is a finite automaton, a deterministic finite automaton, or a grammar, the same thing for the soft constraint, we get polynomial time algorithms in some of these cases. But for more complicated ones, the problem becomes hard. So for non-deterministic automata or for ambiguous grammars, or actually even if you have unambiguous grammars, but both the hard and soft constraint are given by grammars, the problem becomes essentially equivalent in complexity to the class sharp P, the counting problems. So we still actually, in that case, have approximation algorithms for the problem. So for instance, if your specs are Boolean formulas, then this is clearly sharp P hard. But using SAT solvers and recent techniques for approximate counting and sampling, we can still give approximation algorithms for the problem. Okay, so this was all in the static case. If you want to solve this in the reactive case, it's interesting. Feasibility, again, reduces to counting. You can think of it as, you want to find a winning strategy in the synthesis game, but now just finding a single strategy is not, is not necessarily enough. It could be that maybe the adversary can force you to play in only one way to win. If there's only one way to win, then again, you can't have a randomized policy. So there, in fact, need to be sufficiently many ways to win that game. And the result we get is actually extremely similar to what we had before. It's just now, instead of the size of these sets I and A, we have this new notion of size, which we call the width. And the way that works is the width basically counts the number of winning plays minimized over all possible adversaries. So here's the definition. What we say is we maximize over all possible strategies for us, the improviser. Then we minimize over all strategies of the adversary of this inner quantity. And this notation here is saying the probability of getting a particular trace, W, given the strategies of the two players. So what we'll do is count what are all the traces that have non-zero probability given these two strategies. And we want to make that as large as possible, and the adversary wants to make it as small as possible. So this is what we call the width. So the width of X is the basically the maximum number of plays that we can ensure are possible to play, regardless of what the adversary does. So once you have this, we get the same kind of inequalities we had before. Constructing an improviser turns out to be a lot more involved than in the non-reactive case that I described before. In particular, it turns out that the strategy cannot be memoryless, even if you have just like a safety specification where it's known you have memoryless strategies normally. Here, the need to do it randomly actually forces you in some way to need some memory. But the way our strategy works is essentially does a kind of random walk, remembering the widths. So you construct the game graph here, and the numbers that are being shown in this example are the widths. So if you have the winning states, then you have one way to win from there. And so basically, if you minimize at the adversary controlled states and sum at the states you control, this gives you a dynamic programming kind of way to compute the widths. So here we can work out that from the initial state, we have a way to win at least 4 different ways. The adversary may be able to make us win in more ways than that, but certainly we can guarantee at least 4 different ways to win the game. And this gives a dynamic programming way to compute those, and then doing this random walk plus a little bit more complication, because this would be a memoryless strategy. We have to do a little bit more. We end up getting a way to, once you can compute these widths, do an improvising strategy. And so that gives us a similar sort of picture of the complexity. If you have DFA specifications, which includes things like safety and reachability objectives, we can again do this in polynomial time. So we can do like randomized reactive synthesis for reachability games in polynomial time. But for things like non-deterministic automata and even more generally temporal logics, it becomes p-space equivalent. And here, if those of you are familiar with reactive synthesis, may wonder, why is it only p-space for LTL versus like doubly exponential time? It's because of this bounded length window. So everything's in the bounded window, so it's only p-space hard. So this gives you a picture of the theory of control improvisation. And the last thing that I want to mention, I've got like, just a couple more minutes here, so let me wrap up, is I want to highlight an application that was building off some of the ideas I presented here that we've been working on recently, namely using improvisation to design and analyze machine learning systems. So the motivating example here is if you want to test something like a self-driving car, it has a camera maybe that's taking images like this. It's gathering data about a very complex environment. And we'll define the environment configuration, so not the pixels, but the configuration of where these cars are and so forth as a scene. Even if you think at that high level of scenes, not pixels, these have a complex structure. So collecting examples of these real-world scenes is expensive, but it's also difficult to generate them automatically for training or testing purposes because the space of possible scenes is so large. So you've got all types of different parameters, like the positions of the objects, the types of objects, and so forth. So it's a very large and unstructured space. If you just generate randomly, you'll get things that don't really make sense physically. Realistic scenes have complex geometric constraints, like cars tend to drive in lanes, for example. And furthermore, you might be interested in particular types of scenes, like highway traffic, bumper-to-bumper traffic. So you want to generate only things that meet your specifications. And so that's, again, it's reminiscent of an instance of control improvisation, where we have specifications saying what types of data we'd like to randomly generate. The complexity here, though, is that while we again have hard and soft constraints, like objects should not intersect clearly, we might have a soft constraint, like 20% of images should be at night. We need more complex randomness requirements, like we might want to say that the distance between cars should follow this particular distribution that we learned from data. And that doesn't fit into the definition I gave before. So we need a formalism that can express that type of constraint. And a natural one for that is a probabilistic programming language. And so that's what we've done the last few years, is we've developed a language called Scenic, which is a domain-specific probabilistic programming language for defining a distribution over scenes and the behaviors of the objects in those scenes. So for example, bumper-to-bumper traffic, the example I started the talk with, these images were generated from a short program in Scenic. It's a single Scenic program that we're sampling multiple times and getting these different images from. And Scenic makes it possible to define these kind of complicated scenes easily by giving you concise syntax for common geometric relationships. And the domain-specific nature of Scenic also gives us more efficient sampling algorithms that I won't talk about here, while still giving you the modeling convenience of probabilistic programming by being able to impose declarative hard and soft constraints. So I'm out of time here, so I'll just mention quickly that we have some case studies using this, for example, finding bugs in aircraft control systems, getting confused by shadows, things like that, and then actually fixing those problems by generating synthetic data using Scenic. We've also used these techniques to look at self-driving car software, finding errors in simulation and then reproducing them on an actual test track with the real car. So just to conclude, algorithmic improvisation is a framework for randomized synthesis, which has various applications, including some that I didn't have time to get into in this talk, like fuzz testing, music improvisation, human modeling, and so forth. In particular, it has applications to the design of safe autonomous systems, like through controller synthesis or synthetic data generation. Also, there's applications through human modeling that I mentioned right at the beginning. There's been some colleagues of ours have used this, for example, to learn human models of how humans make lane changes, for instance. And there's various directions for ongoing work that we're working on. For instance, generalizing the problem to allow further types of soft constraints or randomness constraints, more sophisticated than the ones I talked about here. And also in another kind of synthesis, synthesizing Scenic programs themselves from data rather than writing them by hand. If you're interested in this, please go to our website. We have lots of these examples there and links to our papers and our tools. All right, I'll stop here and I'm happy to take questions.
Great talk. I'm clapping for everyone. Daniel, thank you for the nice presentation. I just realized that in Zoom settings, the equivalent of chair standing up is actually chair starting to unmute herself or himself. So let me just give the others. I have a couple of questions that I asked, but I know that I don't want to do this. Is there someone else who would like to ask a quick question?
Actually, I see that Saleh has asked one in the chat.
Oh, please, yeah.
So let's see. So he's asked, right, so the soft constraints, unlike the hard constraints, can be violated to some extent. And what do you define, like the cutoff point between, when it becomes infeasible, even though, you're allowed to violate it to some extent, right? So the idea is that in our definition, let me go back to that. In the definition here, how often you're allowed to violate this, so how often the word you generate is allowed to not be admissible, is controlled by this epsilon. So if there's a way of satisfying it, say, if epsilon is 1/4, then if there's a way of satisfying this constraint 3/4 of the time while still being sufficiently random, then the problem would be feasible. Whereas there's kind of there's a trade-off between the soft constraint and the randomness constraint, because it could be that if you're in a situation like this one here, if you only have 3 ways to satisfy this, say, but if we have a row of 1/4, we can't just generate each of these 3 with probability 1/3. If we did that, then we would always satisfy the soft constraint. But we would generate some things with probability 1/3, whereas we're only allowed to generate things with probability up to 1/4. So here we have to actually throw in some of these inadmissible ones that violate the soft constraint in order to satisfy the randomness requirement. But if we can do that without going beyond this error probability epsilon that we're given, then we say the problem is still feasible, even though we had to throw in some of these things that satisfied this, that violated the soft constraint. Hopefully that clarifies things.
Okay, let's actually stop here. And it was really great talk. I will then send you, ping you about my question later on, because we're already around half an hour after the schedule. So thank you, everyone, and see you again next Monday. Bye.
Yeah, thank you very much, all the participants.
Yeah.
Thanks, and especially the speakers. Bye, guys.
Bye-bye. Daniel, can I ask you now?
Sure.
So you showed us, I think I've seen all your this talk before about Scenic, and I think you